Green's functions for second order ordinary differential equations. More than 50 years ago, when I was a graduate student in a differential equations course, I can remember my colleagues and I sitting around struggling to understand what a Green's function was. All of a sudden, somebody pointed to a green chalk mark on the blackboard and great glee said, "There it is, that's the Green's function." Well, it took a while in my career for me to articulate what a Green's function is. And it's right here, the kernel of an integral operator that inverts a differential operator. And it's not that hard to see if you look at it correctly. You have a simple ordinary differential equation, y prime equals f. You would obtain the solution by a simple integral. Right there, simple integral. If you have a more complicated differential equation, then the integral is a little bit more complicated. It's complicated by the fact that it has this kernel, and that kernel is what the Green's function is. So let's take a look at what a Green's function is. How hard is it to get? Does Maple help you? And so forth. Since we're going to be working in Maple, here are a few initializations that will be helpful. So we do a restart and bring in the intrans package to access the Laplace transform commands. We're going to make use of the Wronskian command in vector calculus and the determinant command in linear algebra. Now, the right-hand side of our second order differential equation will be this function. When we do an initial value problem, we'll differentiate with respect to t, and I'll call that operator LT. And when we do a boundary value problem, we'll differentiate with respect to x, and I'll call that operator LX. Okay, for a first example, the initial value problem, I'll begin by getting a Green's function by Laplace transform. Okay, so here's the problem. This is the differential operator, time derivatives, right-hand side, inert initial conditions. I use Maple, I get the solution to the problem. This way, at least I know the target. I'm going to get this answer. Okay, now I want to think in terms of Laplace transform. Notational device, I alias the transform of y of t to the symbol big Y. This is the echo. And I write the differential equation Ly equals the Dirac delta function. And this is how Maple says Dirac delta. So this is the differential equation that I'm going to take the Laplace transform of. And I use the inert initial conditions, and transform results in this equation, which I solve for y. Clearly it's 1 over, and you can see the 20s squared from here, and the 23s from here, and the 6 from here. Okay, that's the transfer function. This thing is called the transfer function. Its inverse is called the fundamental solution. So I take the inverse transform of that, and I call that v of t. This is what it comes out to be. The Green's function has this structure. 0 if t is less than x, and this function v of t minus x, and t is greater than x. That means that the solution, y of t, is the integral 0 to t of the Green's function times f of x dx, where x is the variable of integration. I do that in Maple, and I get this answer. There is an alternate that you can employ here. You set the differential equation, or differential operator, Ly, equal to delta of t minus x, takes the shift ahead of time. Then the transform of that gives you this expression. When you invert that, you immediately get v of t minus x, which is the expression that we had for v of t minus x if we make that shift here. So now let's introduce a little formalism. Let's see if we can get a recipe for finding this Green's function. So here's the recipe. Let me just state it. Differential operator, general form, linear, second order differential equation. Y1 and Y2, a fundamental set of solutions. So that means homogeneous solutions. The Green's function for inert initial conditions. That's going to show up here. What is that Green's function going to look like? It's going to look like this. Y2, Y1, Y1, Y2. T, X, T, X. 0 for X greater than T. This expression for X less than T. This is the Wronskian of these two solutions. This is the leading coefficient, A0. This is the recipe. Okay, where did this recipe come from? What is its derivation? Now, I've seen derivations of Green's functions that have to do with the method of images, left me totally confused. I always liked the presentation that stems from the variation parameters formula because that stems from what I know about differential equations. So this is a particular solution by the variation of parameters formula. This is the homogeneous solution. Therefore, this is a general solution. And I always taught my students the variation parameters formula 2112, y2, y1, y1, y2, 2112 with a minus sign in between, 21-12. Here's the driving term. This is the Wronskian. This is the leading coefficient. Okay, general solution, you apply the initial conditions. They're inert initial conditions. So y at 0 is 0. So this is y1 at 0. Here you get y2 at 0. When t is 0, you get y2 at 0 times 0. And here you will get y1 at 0 times 0, because t is equal to 0. So what is left is just this piece right here. But now you got to take the derivative, because you can set the derivative equal to 0 at times 0. So how do you take the derivative? So here's y1, you're going to get y1 dot. Here's y2, you're going to get y2 dot. This is a product. You're going to get y2 dot times the integral. Then you're going to get y2 times the integrand. And here you have minus y1 dot times the integral minus y1 times the integrand. Now, if you look carefully, y2, y1, they're both functions of t at this point. y1, y2, they're both functions of t. This term is positive, this term is negative. They cancel out. So you have this term, a y1 dot evaluated 0, b y2 dot evaluated 0. This term, y2 dot at 0, but you have to put a 0 in up here, so the integral becomes 0. This integral here is going to become 0. What's going to be left? This is gone. This will cancel with this, because it's 2, 1, 1, 2, positive, negative, they cancel. So all that's left is this. Well, you have this piece here, both equal to 0. So it's a linear system, homogeneous in A and B. The Wronskian can't be 0, because then you don't have a fundamental set. So A and B has to be 0. Consequently, this A and this B are 0. And all that's left of the general solution is this piece. And so I've written that piece here. And that's what gets massaged into the Green's function. y2 of t on the outside, y1 of x on the inside, y1 of t on the outside, y2 of x on the inside. You'll put the f when you employ the Green's function integral, Wronskian leading coefficient. So let's implement this recipe in Maple. So this is a fundamental set, two exponentials. This is the Wronskian of these two functions. This is what the recipe for the Green's function says to write down. Okay, if you do the y2, y1, y1, y2. So we have this representation of the Green's function, but we also had this representation, v of t minus x. So let us take this expression, put it here. Let us subtract v of t minus x. And we want to simplify that, but in order to simplify it, we first convert everything to exponentials. And then we simplify, assuming that t is greater than x, so that we're down in here, right? T greater than x. And it comes out to be 0. So both approaches have resulted in the same expression for the Green's function. Now I'm going to graph g of x and t and the partial derivative with respect to t. Two graphs. And they will show important properties of the Green's function. This is the graph of g. It is a continuous function, but it is not differentiable across the line x equals t. And here is the graph of the derivative. You see it jumps. And you will notice that the jump is on the order of 0.05. 0.05 is 1/20th, and A0 is 20. So this is the amount of the jump, and this is a characteristic of the Green's function, and you can in fact define the Green's function this way, but it is not illuminating. The remaining 4 examples are boundary value problems. Different sets of initial data or boundary data. So example 2, separated and homogeneous data. Okay, separated means y is evaluated at the left end only in the first condition, and y is evaluated at the right end only in the second condition. This is the general form for such a problem, right? General differential equation, general set of coefficients in the boundary conditions. This is what the Green's function will end up looking like. y1, y2, y1, y2, tx, xt, t less than x, t greater than x. Right? That'll be the recipe we come up with. This will give you the solution. Integrate against the Green's function, a to b, where the a and the b are the endpoints. Fundamental set, y1, y2, but they obey the following boundary data. y1 is chosen so that it satisfies the boundary condition at the left end. And y2 is chosen so it satisfies the boundary data at the right end. So this satisfies one, this satisfies the other. Okay, I've just made some statements here. Now I want to show you where they come from. I'm going to use the over dot to denote differentiation with respect to x, contrary to what I said at the beginning. And the reason for doing that is Maple's typesetting does not get this right. Y prime will either shift the subscript, or if it doesn't shift the subscript, it will shift the prime, or it will raise the prime. It just does not typeset correctly. So I'm going to use the over dot. What are the ingredients that we need here? y1, y2, fundamental set for the ODE. y1 is chosen to satisfy the condition on the left. Remember, these are separated conditions, so you separate. So it applies to the function y1, satisfies the left boundary condition. y2 satisfies the right boundary condition. W is the Wronskian. Here's an abbreviation. F over the Wronskian over the leading coefficient. I'm just going to call that psi. The particular solution comes by variation of parameters. y2, y1, y1, y2. These are indefinite integrals. y2, y1, minus y1, y2, 21, 12, which is what I used to tell my students. So here's the general solution. Homogeneous part, this is the particular solution. But we can dispense with this homogeneous part if we change this indefinite integral to a definite integral. What we do by introducing a definite integral is we pick up a constant. And that constant will multiply y2 over here, and this constant will multiply y1 over here. C and D are not known. We'll figure them out as we go, but we don't have to drag around this homogeneous part. Now we want to apply the boundary conditions to this expression. When we do that, the Green's function will pop out in this form. All right, so let's start working on B1 applied to this y. So here I've written down that y. Now I'm going to apply B1. Well, B1 is the condition on the left. So I need y at A, and I will need y prime at A. So let's see what y at A looks like. y2 at A, integral c to A. y1 at A, integral d to A. That part's easy. Now we have to take the derivative. Look here, you're going to get y2 dot times the integral plus y2 times the integrand evaluated at x. So it's y2 at x, y1 at x, psi. Then you have this term, minus, you're going to get y1 differentiated times the integral. Then you're going to get y1 times the integrand, and the integrand is evaluated at x. And if you look carefully, y2, y1, they're both at x. y1, y2, they're both at x, plus here, minus here. They will cancel. So the derivative has only these two terms, y2 dot at x, the integral, y1 dot at x times the integral. So now you evaluate that expression at A. y2 dot at A, integral c to A. y1 dot at A, integral d to A. If you put it all together in B1y, here's your alpha 1 y at A. Here's your alpha 2 y prime at A. Rearrange the terms slightly. You have the integral c to A, and the integral c to A. Factor that out. That's here. What are its coefficients? A1, y2 at A. I guess that's alpha 1. And this is alpha 2, y2 dot at A. That's this term here. Then you have the integral d to A, one here and one here. Factor it out. The multipliers are alpha 1, y1 at A, that's this term, and alpha 2, that's this one here, and y1 dot, that's this guy here. Okay. So, B1 applied to y2 is what this is. Because this is B1. left-hand side, left-hand endpoint. This is B1, alpha 1, alpha 2, okay? So that's applied to Y2. So this is B1 applied to Y2 times this integral. And this guy is B1, alpha 2, applied to Y1, Y1, prime, times that integral. This has to vanish. But B1 on Y1 is chosen so that you get 0. That's what this 0 is. In order to get this piece to be 0, you pick C to be A. Then this integral vanishes. So that takes care of one of these boundary conditions. Now I got to do the same thing for the other boundary condition. This is the expression for y. You have to evaluate y at b. Then you have to take the derivative. The derivative boils down to these two terms. Then you evaluate the derivative at b. Then you put the pieces together. Beta 1, beta 2. This is the y, and this is the y prime. You shuffle the terms around, factor out the integrals. Okay, a to b here, and d to b here, because we now know what c was. C is equal to a. This piece, beta 1, beta 2, y2, y2 prime. So this is b2 applied to y2. And here's the multiplying integral. And this is beta 1, beta 2. So this is b2 applied to y1. So it's b2 applied to y1 times this integral. But b2 applied to y2 is 0. So this term's gone. Now we need to get this term to disappear. So we choose d to equal b. And we have satisfied both boundary conditions. So if we now go back to this line right here, where we have a to x and x to b, we see why this splits when you are integrating with respect to t, and t is less than x. It's in this region between a and x. It's less than x. You are here. And so you get y1 of t, which is this one, and y2 of x, which is this one. And when you're integrating here, t is greater than x, t is greater than x, and you have y1 at x, y2 of t. And so finally, the mystery of where did this Green's function thing come from is revealed. It comes from variation of parameters. Okay, now we want to get into Maple's solution. Take a look at Maple's solution looks like. We just used dsolve. I call this y maple. This is what the solution looks like, and this is what its graph is. Now let's implement these Green's function calculations for this example. We need two linearly independent solutions that satisfy, in one case, the left boundary condition, in one case, the right boundary condition. And we have two members of a fundamental set, y1 and y2, which are not necessarily going to have that satisfaction property of one on one side and one on the other. So we take a linear combination to form a U1, and a different linear combination to form a U2, and here are those two linear combinations, we apply the first or the leftmost boundary condition to U1, we get this, and we apply the rightmost boundary condition to U2, we get that. So we have these two equations, but there are four constants, R1, R2, S1, S2. We have two conditions. So there's some freedom here in how you choose these solutions. So I solve for R2 in terms of R1 and S2 in terms of S1. And I chose, because there's some arbitrariness here, I chose R1 to be 205. So that made R2 be minus 156. I chose S1 to be 5. So S2 was 16 times this exponential. That gave me two solutions. Instead of calling them U1 and U2, I felt more comfortable calling them big Y1 and big Y2. So here are my two solutions. This is the one that satisfies the left boundary condition. This is the one that satisfies the right boundary condition. Here is the Wronskian. I then paste together this Green's function, which is formed according to this recipe that we saw way back here. It's formed according to this recipe. Y1, Y2, Y1, Y2, Tx, Xt. You paste that together, right? Use that Green's function that I've just constructed and get the solution to this boundary value problem. I call it Y Green's function. And I want to compare that to Y maple. I do it by simply subtracting and simplifying it. I get 0. So these two solutions are the same. Green's function stuff worked. So we've gotten this Green's function. Let's take a look at some of its properties. Analytical and graphical. Here is the graph of G. It's a continuous function. The piece where x is less than t is here. The piece where x is greater than t is here. You'll notice that the line x equals t is the piece where these two pieces are pasted together. Analytically, you're looking at as x goes to t from the right, as x goes to t. So x is always greater than t, so you're coming in this way. And this limit, you're coming in this way. They match. But for the derivative, they don't match. You can see here there's a jump. And it's a uniform jump. And it's 1/20th. You can see from the scale 1 over A0, discontinuity in the first derivative, the derivative with respect to x. Third example, separated but not homogeneous boundary conditions. So instead of having zeros on the right-hand side, we have non-zero. I chose 9 and 4 for my example, alpha, beta for the general case. This is the Green's function for the homogeneous boundary conditions. And what you do is you add on this little chunk to the solution of what's the solution to the problem with homogeneous boundary conditions. And again, y1 satisfies b1 y1 equals 0, which satisfies the left boundary condition, and y2 satisfies the right boundary condition. Let's get the maple desolved solution so we have something to compare to when we get our Green's function solution. Y maple, homogeneous, right? Non-homogeneous boundary conditions. So you just put it into DSolve. This is what you get back, and this is what the graph looks like. Now we have something to compare to when we do Green's function. Now let's get the solution by this Green's function strategy. The perturbation term that we can construct is P, and that's constructed according to the recipe that we presented here. This is what it will look like. You add that to what's essentially the homogeneous solution, or the solution to the problem with homogeneous data here. This is what you get. And we make the comparison. So you got, this is Y maple from previous example, example 2. Homogeneous data. This is the perturbation you add on to make it work. This is Y maple non-homogeneous with a non-homogeneous data, and the difference is 0, so it works. So let's just take one last look at this perturbation term and see why it works. This piece satisfies homogeneous data. When you apply B1 to this term, you get B1 on Y1. B1 on Y1 is 0. Over here, you get B1 on Y2, which cancels this B1 on Y2, leaving alpha. So when you apply B1, you will get alpha. When you apply B2, you get B2 on Y1, which will cancel this B2 on Y1, leaving you just this beta. And B2 on Y2, 0. And this term drops out. So the perturbation is the right piece to add on. Example 4. Example 4, mixed boundary data. But we'll start out with it being homogeneous. By mixed, we mean you have Y at the left end and Y at the right end appearing in one boundary condition. And the same thing happens in the other boundary condition. Y at the left end mixed with Y at the right end into one boundary condition. General form of the differential equation, general form of the data. Green's function will have two chunks called GA and GB. This chunk is for t less than x, and this chunk is for t greater than x. When you get the Green's function, then you can solve the problem. So again, let's just get a solution from Maple's DSolve command, so we've got something to compare to. This is what the solution will end up looking like. This is what its graph will be. Y maple mixed homogeneous. So how do we get these two chunks of the Green's function? This thing called GA and this thing called GB. We begin with a fundamental set. Take one linear combination and call it GA. Take a different linear combination and call it GB. Now, write the boundary conditions, which are mixed, in such a way that the A part is here and the B part is here in each of the two conditions. And so it would look like this. The A part, the B part. The A part, the B part. we apply the continuity condition that the A part and the B part have to be continuous. And we apply the jump condition. So the jump is 1 over A0. If you just say G here and G here, generic G, you're always scratching your head saying, which piece of G do I deal with? So I've written here you are taking GA, and here you are taking GB. Then you apply the boundary conditions in the following way. This piece of the boundary condition is applied to GA, and this piece of the boundary condition is applied to GB. And then this piece of the boundary condition is applied to GA, and this piece is applied to GB. This is the continuity condition. This is the jump condition. 4 equations, 4 unknowns. 4 unknowns are R1, R2, R3, R4. Obtain the solution to those 4 equations, and you can construct GAGB, and therefore you can construct the Green's function. Now let's implement this strategy in Maple. Two different linear combinations of a fundamental set. 4 constants, R1, R2, R3, R4. Call this chunk QA, which is the GA, QB, which is the GB. This is the split for the boundary conditions. Boundary condition 1, 2 chunks. One chunk that applies at A, one chunk that applies at B. Second boundary condition, 1 chunk that applies at A, 1 chunk that applies at B. You apply B1 at A to Q at A, plus you add on B1 at B applied to QB. And you do the same thing here for the second boundary condition. B2, you apply it to this, and you add on B2 applied to that. That gives you these 2 equations, and you'll see there's R3, R4, R1, R2 in both equations. So these 2 equations have 4 of the unknowns. This is the continuity condition. 1 more equation. This is the derivative condition. So now you have 4 equations and 4 unknowns. You can compute R1, R2, R3, R4, and hence you can put together a Green's function. This is what the Green's function looks like. Now I'll use the Green's function to compute a solution. Y Green's function mixed homogeneous. So this is the solution that we obtained from the use of this Green's function, which we obtained from this recipe that we just went through. Compare that to the Maple solution. Y Maple mixed homogeneous. Compare, difference, 0. The Green's function stuff works. Let's take a quick look at the graphs of G and its derivative. The graph shows that G is continuous across the line x equals t. The derivative has a jump of 1 over A0 across that same line the way it should. A distributional approach to constructing this same Green's function works here because the coefficients are constants, and so we can use the Laplace transform and the delta function stuff will work. But we don't know initial data, so we treat those as unknowns. Y at 0, rho. Y prime at 0, sigma. But we take the Laplace transform of the distributional equation, delta of x minus t, solve for y, the transform, and you'll see you have a rho here and a rho here and a sigma. So you get the transform back in terms of these 2 unknown constants. Invert that transform, constants included. But now you apply the initial or the boundary data. So you apply the boundary conditions and you get two equations in rho and sigma. This is what you get when you apply the first condition. This is what you get when you apply the second condition. You solve those two equations for sigma and rho. Put the values back into y. Convert the Heaviside functions to piecewise. Convert hyperbolic sine, hyperbolic cosine to exponential form. You get this Green's function. This chunk, this chunk. Compare this distributional version with the G that we got earlier. Make the conversion to piecewise, simplify. They are the same. So you have a variety of techniques at your disposal to investigate these Green's functions. Our final example will have mixed boundary conditions, but they will be non-homogeneous. And so I think you might expect this perturbation stunt to work here as we worked it earlier. So mixed boundary conditions. But now they're not homogeneous. I use 9 and 4 again. So in general, it will be alpha and beta. So this is the Green's function solution to the previous problem. This is the perturbation term. Choose the fundamental set so that B1 applies to Y1 and gives 0. And B2 applied to Y2 gives not 4 but 0. And so there's the perturbation. Let's see if that will work. Well, as before, we'll get a maple desolved solution just so that we have something to compare to. Maple, a Y maple, mixed, non-homogeneous. This is what the solution turns out to be. This is what its graph looks like. And then we'll see if we can get the same thing from a Green's function approach. Now let's see if we can get a solution to this problem through this Green's function approach. Okay, so what we're going to do here is we're going to write the boundary conditions. We functionalize the boundary conditions to make them easier to apply. We did not split them because that was done in the solution with the homogeneous data. We don't have to do that here. Just for convenience, we have these functionalized versions of the boundary conditions that we can apply. We have a fundamental set, which are these two exponentials here, and we take two linear combinations. Call one QA and we'll call one QB. We'll apply these two boundary conditions to QA and QB. You'll notice that the first boundary condition is applied to QA, and it will contain just R1 and R2. See, R1, R2, R1, R2. And the second boundary condition is applied to QB, R3, R4, and R3, R4, R3, R4. So we can solve for two of these constants in terms of the other two. I solved R2 in terms of R1 and R4 in terms of R3. And since there's some arbitrariness here in how you construct these two solutions, I have picked R1 to be 5/4, so this fraction will cancel out from R2. And I have chosen R3 here to be 5/2, so that fraction cancels out of R4. That gives us this new fundamental set, Y1, Y2, which are what these two things become when we put in those coefficients R1, R2, R3, and R4. From these two solutions, we construct this perturbation according to this recipe up here. Then add that perturbation to the solution from example 4 where the boundary conditions were homogeneous. So we have this solution. So here is the solution with the homogeneous data. Here's the perturbation. Here is the solution we constructed with maple. Why maple? Mixed, non-homogeneous. Difference is 0. Again, this Green's function stuff works.